In this video, I want to discuss the numerical classes in Haskell, classes that are used to represent numbers. I think the general consensus is that the class hierarchy that is used for numbers in Haskell is mostly historical, and if it were redone now, it would probably be done in a better and more systematic way. At the same time, any change to a part of the language that is so widely used everywhere would also break an amazing amount of code. That is why people are reluctant. But I take into account that things are not really as good as they could be. Some things are nice. I mean, so for starters, something that we have already seen a number of times is that literal numbers are actually overloaded themselves. So if you just type a number literal, then you get something that is actually overloaded over the num class. And again, we have the situation with the target type being overloaded. So it's the context in which we use something which affects what type this is actually going to be. So this means that we can use a literal like 2 in a context where we expect a double, and then we get a floating point number. And we can see also that the show instance for double is always printing a dot and a 0, even if we have something that happens to be falling into the integral subset of the doubles. And if we say that this is in a context where this is an integer, then it can be used as an integer. A similar thing applies to fractional literals, actually. So if we have a look at a literal such as 2.5, it also, we won't get a type inferred that says this is a double. It will say that this is anything that belongs to the fractional class. So, and there are still different types that belong to the fractional class. And we'll see that. So let's see what kind of classes play a role here, and what methods do they have, and what kind of types play a role. So I guess the most important class in the context of numbers is the num class. And we see that the num class has methods plus, minus, times, right? So addition, subtraction, multiplication. Then it has negate, and I think I have once briefly mentioned that negate is another name for the unary minus. So negate computes the 0 minus the number that we are providing. Then we have a function that computes the absolute volume, and then we have a function signum that computes +1, 0, or -1, depending on whether a number is positive, 0, or negative. And then we have this function from integer, and that is taking an integer into something of this type. And then we have a minimal pragma, which is actually a little bit complicated, so we have to give at least plus, but not minus, times, abs, but not negate, the signum from integer. And then we still have to give negate or minus, one of the two. And conceptually, if we define negate, right, then we can define minus as an addition with the negated second number. And if we define minus, then we can define negate as 0 minus the other number. But we have to give one of the two. In general, num instances are rarely defined for new types, but it is possible. And it's one of the interesting things in Haskell that you can define your own number types or number-like types. And let's have a look at what instances we already have to work with. we have int, integer, float, double, and word available as a basis. So let's first talk perhaps about int and integer, which I think I've briefly mentioned before, but probably not in very much detail. So an int is a 64-bit bounded integer. So with overflow and whatever, assigned 64-bit integer on today's machines. In fact, I think the Haskell standard is only saying that it must be at least 32 bits. But in these days, I think it's mostly consistently 64-bit. And so that means that, for example, ints are also an instance of the bounded class, and we have a maximum value, and we can, sorry, now the type signature does not scope correctly. We can add one to this and get an overflow, and so on and so forth. So these are our integers. Whereas integer, spelled out, is not an instance of the bounded class. So if we ask for the max bound of integer, this is not an instance of the bounded class. And if we, in fact, take the max bound of int, and I just copy this number, and I add 1 to it, and I say I want to treat this whole thing as an integer addition, it's perfectly fine. And I can get far larger numbers. Right? Another thing that you can try is you can compute the product of the numbers from 1 to 50, and you can try to compute that as an int, and you get a negative number indicating that something has gone wrong, and you apparently have had an overflow somewhere. Right? But even if you got a positive number here, it would be not clear that is the correct result, right? And we see if we compute this as an integer, we get, in fact, a much, much larger result. But this is fine. So integer is actually just bounded by the size of your memory. Small integers are still very compactly represented, but not quite as compactly, of course, than a built-in 64 integer. Larger integers take up more memory correspondingly. Computation with integers is a little bit slower than computation with ints, but you never have to worry about overflow. Otherwise, ints and integers support pretty much the same operations, which is why there is another type class that basically unifies these two. We'll see that in a moment. Or, well, these two and possibly more. There's also word, we can see here. Word is an unsigned 64-bit integer, so word is also bounded, but the min bound of word is just 0, not a negative number. The max bound of word is a correspondingly slightly larger number, and if we add 1 to this on words, we get an overflow on words, which starts from 0 again. Okay. And then we have floats and doubles. These are single and double precision floating point numbers. In general, I think double is used far more widely in practice and Haskell libraries than floats ever are. So I would generally not recommend using floats at all. And I think that's concluding the num class and what we have to say about this. So let's look at the integral. Oh, well, no. Sorry. I should talk about from integer again. From integer is actually the method that is being used for these overloaded literals. So if you think about what does it mean for literals themselves to be overloaded, they are not a member of this num class. So, but the literal can always be seen as an integer, as an unbounded integer. Like if you write a sequence of numbers, right, it's always rather trivially a legal member of this only memory bounded type of integers. And now, since the num class has this method from integer, we have to explain how to go from this unbounded type of integers into our possibly more restricted type of that we are currently considering. Right. So if we interpret an integer literal as something else, then this from integer method is implicitly called. And additionally, we see here that we get a warning that in this case we had an overflow in this implicit conversion that goes from this integer literal into the type that we are applying. So that is fortunately warned about additionally. Okay, so this is actually something that older GHC versions haven't done, but the recent GHC versions thankfully do. But it is in principle the from integer method that is being called here. If we explicitly call this method, so if I take from integer, then I don't need to give a type annotation on this integer literal. That is now forced to be an integer, but on the result type, I would still want to give an annotation such as word. Then I'll get exactly the same result. So this is the function that is being called to interpret integer literals, and this is what is allowing us to use overloaded literals in a particular context. Now let's look at the integral class next. The integral class is for types that are integral, such as int and integer and word. And all of these are supporting similar operations, and there are a couple of operations that are being listed here. And in particular, I think the most important operations are these integer division operations, such as mod and div, and rem and quad are relatively similar. They behave slightly differently from each other if negative numbers are involved, but as long as you're only using positive numbers, then div and quad are behaving exactly the same, and rem and mod are behaving exactly the same. They're often used infix, so if you divide 10 by 2, you get 5, right? Because that is a division that works without a remainder. But if you divide 10 by 3, then you get 3 rounded down. So this is always going to be rounded down. Right? So similarly, if we divide 100 by 7, then we get 14, because 14 times 7 is 98. Right? If you want to know the remainder, we can use mod. So 100 divided by 7 is, as we've just seen, 14 with a remainder of 2. So mod gives us that remainder. If we want to do both at the same time, we can also use this div-mod combination, which gives us the 2 results as a pair. So see that we get 14 with a remainder of 2. Again, this works for int and for integer and for word in the same way, only that, of course, for int and for word, you have to, in principle, in general, deal with the possibility of overflow. Note that if you divide something by 0, you'll still get a crash. So this is a partial function, which I'm not so harsh about, because I think in general this case of division by 0 is a bit easier to rule out, but in general you should still be very careful, right? I mean, in general, you don't want to divide by something that you don't know, that you cannot rule out to be 0, but often these kinds of divisions are used with a concrete constant second argument anyway, and then if that is not 0, that is totally fine as an application. So I think that's probably already all we have to say about integral. And then we have a number of type classes that are used for non-integral numbers. I think the first and most interesting one perhaps is the fractional class, because it contains the division operator. So the division operator is, well, as you would think, and then there is this recip function, which basically computes the 1 divided by version. So 1 divided by 2 is 0.5, 1 divided by 0.5 is 2.0. And the primary instances of the fractional class are float and double, but there is an interesting type that is not exported via the prelude, which is also an instance of fractional, and I do want to advertise that somewhat, and that is that type of rational numbers. And this is very interesting because, as I said, literals with a dot are also overloaded, so they can be used as doubles and floats, but they can also be used as rational numbers. And rational numbers are internally a data type that is represented, if you look at the info, is represented as this is a complicated infix constructor, which is ultimately just written %, but this constructor is actually hidden, so you're not supposed to use it directly, but it is written as a fraction of two other numbers, typically integers, a fraction of two integers. So in particular, the rational type is a ratio of integer. So you have two integers here, a fraction of two integers. And that gives you a way to represent fractions precisely without any rounding issues. And at the cost of not having certain functions available, in particular, trigonometric functions such as sine and cosine, or I think that's probably and square roots and stuff like that. So there are certain functions that are not available, but as long as you don't need them, you can avoid having any rounding issues by just going to rational, and it's certainly worth a consideration. In particular, all sorts of financial calculations are typically much more nicely done using rational numbers, in my experience, or even using integers with a fixed precision than by using doubles and having to deal with potentially lost fractions of a currency unit or something like that, or invented fractions of a currency unit. So there's rational type is interesting. So, and in particular, if we know that we have overloaded literals, we can also do something like this, and indeed we see that the number 0.5 is automatically reinterpreted to be the fraction 1/2. Or if we do something like a slightly more complicated number, then automatically reinterprets this and applies optimization of the fractional representation as well. Right? So, and you can calculate with rational numbers just as with other numbers as well. And many contexts, they're really just as convenient to use. So there's also this from rational function, which is used for the fractional literals in the same way as from integer is used to for the integer literals. And this is going from rational because, in fact, whenever you have a literal with a dot in it, it can be precisely represented as a rational number by finding the appropriate power of 10 to divide this number that you have written here by, in order to generate the precise representation. And so you can always go convert precisely a literal fractional number into a rational number, and then you can go from the rational number into the possibly more lossy double or float representation, right? And so if we take something, let's see, just something relatively random, and long, and we say we want to interpret this as a rational number, we get this. If we say we want to interpret this as a double, you can see that we get a somewhat lower precision, and if we interpret this as a float, we see that we get yet again a somewhat lower precision. I'm actually currently not 100% sure whether the shown precisions by the show instances are actually the full internal precision, or whether there is more available, but nevertheless, I mean, this is basically giving you an idea, right? Then there are some more classes that are giving you other commonly used methods. So there is this floating class, which is implemented by float and double, which is giving you trigonometric functions and exponential functions. So you get exponential, logarithm, square root, pi, sine, cosine, all the things that you would probably expect. And there are things such as real frac class that gives you rounding functions. So in general, one thing that you probably do want to do occasionally is to either convert from an integer into a floating point number, or the other way around. And in order to convert from a floating point number back into, or also a fraction number, also a rational number back into an integer, you have to make a decision. So you would typically use something like floor or ceiling to specifically generate the next smaller or the next larger integer number. So for example, if you do floor of 3.5, you get 3, right? And that is a way to convert a double or a rational into an integer if you need this. And you can see that it goes from something that is in the real frac class, which means in particular it goes from a rational, a float, or a double, to something that is in the integral class. So that could be int or integer or word. And the ceiling of 3.5 is correspondingly gives you 4. There is also the round function. The round function, depending on, like, different countries have slightly different cultures with rounding. The definition of the round function may be a little bit unusual. It, in principle, rounds to the closest number, right? So 3.3 is closer to 3 than to 4. So that is giving you 3. 3.7 is closer to 4 than to 3, so that gives you 4. But what does it do with 3.5 exactly, which is equal distance from 3 or 4? And there round takes the perhaps slightly unusual approach to round to the nearest even number. So it doesn't always round up or always round down, but it rounds towards the nearest even number. So in the case of 3.5, the nearest even number is 4, so it will round up. In the case of 4.5, the nearest even number is still 4, so it will round down. For 5.5, it will round up again, and for 6.5, it will round down again. The idea is that it is overall a little bit more fair, if not all 0.5 fractions are being rounded up or rounded down consistently. So the other direction of conversion, if you want to go from an integer to a floating point number, that is usually done using this from integral function. From integral is taking an integral as a source and has an arbitrary numeric type. In particular, can have a double type as the target, or a rational type. So you can use from integral to explicitly convert from an integer to a double if you need that. Okay, so because of the nature of the overloaded literals, very often you don't actually have to apply explicit conversion functions, because if we say combine 2 and then 2.5, the context automatically makes it clear that we are in a fractional context. So even though this is a potentially an integer literal, the presence of this literal makes it clear that we are suddenly now cannot be in an integer context, so we don't actually have to provide an explicit conversion. But sometimes in combination with other functions, we still do. So for example, if we have the integer division of 5 and 2, then we also get 2 out, but the type of 5 divided by 2 is restricted to be a part of the integral class, because we have already been applying the division function, which restricts its argument to the integral class. So the type of 5 divided by 2 is more limited than the type of just writing 2. So if here we are replacing our 2 with 5 divided by 2, then suddenly we get a type error, because now we have conflicting constraints and it is no longer clear which type we mean. Here we are having something that is restricted to the integral class, and here we have a fractional literal. So what number type are we actually supposed to use? Because like basically the world of integral types and the world of fractional types is disjoint. So at this point, we probably really want to explicitly convert this this part here from an integral type into a fractional type, and we can do it like this. We don't even need the parentheses here, because it's a function application that binds stronger than the operator. So sometimes you do need these conversion functions if you combine functions in such a way that they are that their result types are suddenly becoming too specific, and the overloading is not doing the resolution for you appropriately anymore. There is never any implicit coercion going on in Haskell, right? The only kind of things that feel a bit like coercion are to do with overloading. That is, that something is still flexible between multiple types. But that means that its type has never been completely determined yet, so you can still make a choice. If something is at some point of one concrete type, int or double or something, that remains at that type. If you want to change it into something else again, you have to apply an explicit coercion function, such as from integral or floor or something like that in the other direction. Now, there's one more thing I want to mention, and that is that something I've been glossing over so far, that in the context of number types, we also very often see defaulting being applied. And defaulting in the context of number types is applied not just in GHCi, but even by Haskell. And it is somewhat confusing. And again, if you enable warnings, if you enable all warnings, which is generally a good idea, then GHC will warn you about this. And this is a redundant import warning. And if I enable this for, let's say, for the interpreter as well, you see that I suddenly get all sorts of warnings. And why is this? Well, because even if I just type the literal 5 now, which we've always been glossing over, right? It's actually an overloaded value, right? It is the number 5, but it is actually has the type num p double arrow p. So what instance do we mean, right? What is the instance that we mean? And we have to make a choice, because we have not provided contextual information. If I explicitly say I want this to be an int, or if I explicitly say I want this to be an integer, then that's fine. But now, if I type a very large number, which of the two does it actually use? Does it use int or integer? And it may make a difference for overflows, right? And we'll see by enabling the warning that it defaults when it can, to integer, not to int. So the preferred choice for num-class overloaded things, if a choice has to be made and the contextual information is not explicitly present, is integer. That is what GHC does. And the preferred choice for something of a fractional class type, again, 2.5 is overloaded. And which choice it makes for the concrete type may make a difference for the calculation, right? It's different whether I add two rational numbers or two doubles. The preferred choice for fractional class things is double. So, and we can again see this from the warning. If we don't want this, we have to either provide an explicit type signature, such as rational, or we have to put it in a context that makes that type clear, right? Yeah, I think that is probably a useful introduction that covers the basic types that you want to deal with. Int, integer, that really depends on a case-by-case analysis. Ints are much more efficient, but if there is any concern about ints becoming large, you may want to use integer and not worry about overflows, right? Double is probably better than float, but you should also always consider that there is rational available, and if you don't want to worry about rounding errors, it's a very attractive choice. Again, rationals cannot be as compactly represented as doubles, but very often that is not a big deal. Another option, if you want to avoid rounding errors, is just to use fixed precision number types. You can either use integer with a agreed precision, or there are actually other libraries in Haskell as well for fixed precision fractional numbers. And then what we said about conversion is important, right? From integral to go from integers explicitly into the realm of fractional numbers, and functions such as floor or ceiling or round to go from fractional numbers back to integers. And then that defaulting actually plays quite a role. I mean, it's very often used, and it's usually a better idea. That's also why it's a warning to be explicit, to provide the extra type information in such situations and get rid of the warning by adding in either an extra type signature somewhere or an extra type annotation on some sub-expression to make it clear and obvious which of the many numeric types you mean. But because literals are overloaded and many of the operators involved are so flexible, if defaulting wouldn't take place, many expressions actually would need extra type signatures, even just if you type them into GHCi, and that's why defaulting is there and is using integer preferably or double preferably for integral or fractional numbers respectively to essentially provide a little bit of convenience, but at the risk of causing some confusion. Okay, that's it for now.